bloodshed. That's 2 talks in 2 days where I've been the last person to speak. Yesterday was 9 p.m. So I'm going to talk about some lattice results from the fast sum collaboration. We've got a large number of people across many countries across the globe. This picture, of course, is Swansea, tropical Swansea, on a typical day. So the overview of my talk, I mentioned the phase diagram of quarks, or matter. Talk about the lattice approach and why it's really required to use the lattice approach to study the sort of physics that we're interested in. Talk a bit about hadrons and our collaborations approach, and particularly then apply the lattice approach to the study of hadrons at finite temperature. So, to set the scene, we know about water. There's ice, there's liquid water, and there's steam. So this is actually the phase diagram of water, pressure and temperature. The blue part is the solid phase. In fact, there's 12 or so different phases of solid ice, apparently. So it's quite a rich structure. So our idea is to try and map out the same kind of thing, but not for water, not for H2O, but for quarks. And it turns out, as has been discussed by many, many people, that the phase diagram of quarks, or of the strong interaction, QCD, is incredibly interesting as well, but it's far less known than the phase diagram of water. So here is a kind of sketch of the phase diagram of quarks. Here's temperature this time on the vertical axis. And this is baryon density, so basically the matter density, the number of quarks per cubic centimetre, effectively. So you and I are sitting down here, very low temperatures relative on this scale, and quite modest baryon densities. Way out here are neutron stars, so relatively modest in temperature, but very, very large density. And up here, in this region coming down here, that's probed by the heavy ion collision experiments. I'll talk about them later on. The Big Bang is way up here, quite not very dense, but very, very hot. And everything out here looks a bit weird. It's got colour, and it's a quark gluon plasma, where the quarks, which are normally confined into hadrons, become basically free and become their own individual states, unbounded. So that rich diagram, which is not at all fully understood, all comes from this simple Lagrangian. So our aim is to try and study that Lagrangian and try and predict this phase diagram. So even though I'm a theoretician, it's part of my contract to mention experiments once per year. So this is it. So heavy ion collision experiments are done in 2 different places in the world currently. In the RIC, which is relativistic high energy collider experiment in an old army base on Long Island in the US. And this is the Large Hadron Collider, and the actual detector in that, which is designed to study heavy ion collision experiments, is called ALICE. ALICE stands for A Large Ion Collider Experiment. So once a month, every 2 years, instead of protons colliding head-on in the Large Hadron Collider, lead nuclei are injected and they collide head-on. That's what you get when silver nuclei collide inside RIC, and that's what you get when lead nuclei collide. So it's an incredibly complex interaction. The multiplicity of number of particles is hundreds and hundreds, not thousands. So it's very, very difficult to study. Furthermore, as you can imagine, once the nuclei collide, they are flipped over into this hot phase, deconfined phase, and then they expand and cool, and that deconfined phase only lasts for a fraction of a second and expands to a few times the size of the nuclei. But that's obviously in a region where there are no detectors. So all the detectors, everything you see there, is the result of the hadrons and everything else flying out once it's gone back and flipped over to the confined phase. Okay? So if you think about it, you couldn't actually put detectors where it's in the deconfined phase, because the silicon detectors would melt. Okay? It wouldn't be solid. So you're always looking at smoke and gun. You're always looking at the events which happen a stage or 2 after the quark gluon plasma. So it's technically a very, very difficult thing to study. Okay, so the experimenters have got a hard job. Theoreticians do as well, because the force which binds quarks together, which we all know is very, very strong. The string tension, the force which binds one quark with another quark inside a hadron, is 15 tons, 3 elephants. So at kind of hadronic energy scales, it's too large a force to use perturbation theory. Perturbation expansions just don't work. So you can't use perturbation theory. So we discretize the physics, we discretize the mathematics, and don't make any approximations apart from that discretization. And we put it on a DiRAC machine, and we use that to study the physics. So that's the motivation for using HPC. So, in a little bit of detail, we've had quite a few talks on the lattice approach, so I think you might have a take on it. So we discretize space and time and the action and all the mathematics. So continuous derivatives become finite differences. So there's our lattice. And then what we do is we study a hadron on it. How do we do that? Well, we insert an operator there, and we insert its kind of mirror image there to kind of create and destroy that hadron. And then we look at the correlation function between those 2 points. So a very rough analogy is if you had a big bass drum and you hit it with a blunt stick, it would resonate in all sorts of different modes. But if you left it long enough, all the higher frequency modes would decay away, and you'd just be left with the fundamental, the lowest frequency mode. And that's what happens here. If you whack the operator there, you get all sorts of states created with the right quantum numbers, matching the common numbers of the operator you put down there. But all the excited states in that whole tower of states. If you wait long enough, just the lowest mass state, the lowest frequency state, remains, and that way you can just study and home in on that ground state. And so that's what we try and do. You have to wait for a long enough time. And it turns out, because we're in Euclidean time, that everything decays exponentially. So we study this correlation function, where there are 2 operators, and on a log linear plot, you see a straight line. So the correlation function does decay exponentially, and literally the gradient of that is the mass of the ground state. So this makes it sound really simple, so the lattice should have solved everything by now. Why hasn't it? Well, there's a famous sign problem. So when you go out to non-zero barrier density, or strictly speaking, non-zero chemical potential, our approach, our standard lattice approach, which is a Markov chain and an accept-reject Monte Carlo approach, relies on a probability interpretation of what's going on. And as soon as you go out here, you don't have a real valued probability, so you can't use that accept-reject. And the inherent algorithm falls apart. So that's the famous sign problem. So you go a little bit into there, but you can't push it too far. So there's all sorts of different ideas to try and get around that, which I certainly won't have time to talk about. But I just want to point out that it's not as easy as I might make out. So because quarks are deconfined above a certain temperature, we have to think differently. So at low temperature, and low chemical potential, quarks confine, you can do things fairly accurately. All the states are discrete, so it has similarities with atomic physics. We get electronic states which are discrete, and it's a discrete spectrum. The fundamental properties, things like masses and how different states transition into or decay into other states. And the asymptotic states are certainly hadrons. You need a different mindset at non-zero temperature or chemical potential. Of course, we can find all hell breaks loose. You're likely sometimes to get 20% in some quantities because it's very difficult to study. It's no longer like atomic physics, it's more like plasma physics. These quarks and gluons moving around. You don't have down states when you think about things called spectral functions. The sort of quantities you're talking about now are the thermodynamic quantities like pressure and so on. And the asymptotic states clearly are the quarks and the gluons because they're not confined. So these are kind of schematic. So this is in the continuum, and on the lattice, this is non-zero temperature and zero temperature. So at zero temperature, you've got this nice diagram here with the nicely decaying exponential states. Here, you don't get an exponential decay anymore because it's plasma and you get all sorts of weird effects going on. Okay, so we're nevertheless going to push on and study quarks on the lattice. So all the particles in the known universe, we are going to talk about the QCD-like particles, so they're the quarks and the gluons. And we are basically combining the quarks into hadrons and using the lattice approach. in principle, we can study any of those 6 quarks in principle. In practice, there are some difficulties. What we're going to be studying is just combining 3 quarks together, so baryons basically, and we're just going to be concentrating to start with the lightest 3 quarks, so the up and the down and the strange. So you're constrained because I said they're baryons, there's 3 quarks, and you're only allowed to use we're only studying up and down and strange quarks. And it turns out the group structure breaks up into 2 distinct families. One is spin half, the other is spin 3 halves. And the normal way of pictorially representing these is like this. So you've got different quantities of strange quarks going vertically. As you have more strange quarks, you've got to have less light quarks. That's obviously true because there must be 3 in total, 3 quarks in total. And left and right, you either got more D and less U, or more U and less D. So in principle, we can study those 2 entire families, but in practice, it's very much more convenient to use the approximation that the U and the D quark are the same. Okay, so in physics, in nature, they're very close to being the same, so it's not a bad approximation. So everything collapses this way, and we can study that, or that, or that. Okay, we don't differentiate left and right. So that's what we do. In a bit more detail, here are the kind of parameters which we use. Now, the most important thing I want to show you here is this thing on the left-hand side. So normally, lattice practitioners break up their space and time so that it's isotropic, so the lattice spacing in the temporal and the spatial direction are the same. The fast time collaboration and a few others, not many, have it anisotropic, and that means we sample in our time with a lot more data points. So obviously, we hopefully get a better, more accurate signal. So that's an anisotropic approach. It turns out, somewhat counterintuitively, that if you want to impose a temperature on the lattice, you kind of have to shorten the lattice. So the temperature is inversely proportional to the length of your lattice in the temporal direction. And so if you want a large temperature, you want a short lattice, and if you still want a signal, you better have lots of data points, so that kind of motivates you having an anisotropic lattice as well. So here are our parameters, so that's the number of lattice points in the temporal direction, which is inversely proportional to the temperature. That TC thing there is the deconfining temperature. So above that temperature, so down here, the quarks become deconfined. I better move on. So that's a nice cartoon of our parameters. So this represents a quark mass, and this represents the lattice spacing in the temporal direction. So that's nature's value, and we are going to be talking about the top 2 parameters on the right. Ideally, we'd like to move to there, which is running at physically light U and D quarks, and obviously we'd like to move down vertically as well to get fine and fine lattices, and one day we will. Okay, so we study baryons, 3 quarks, and we're going to look at the different types of baryons. And it turns out there's another important quantity for baryons, which is parity, a quantum number. And in nature, the 2 parity states for baryons are not degenerate. So they've got different masses. So for the nucleon, the proton basically, that's the mass of the proton for the positive parity, but its negative parity partner is distinctly different. It's 50% away in mass. And the question is, that's the value at 0 temperature. Is that also the value as the temperature increases, or does something funny happen? And there's theoretical hints to suggest that those 2 masses should coalesce and become degenerate. So we can just study correlation functions of these baryonic states, in particular paying attention to what parity they have. A little bit of technical details. It turns out that the positive and the negative parity states are encoded in the same correlation function, and all that happens, missing a bracket there, the forward and the backward moving part of the correlation functions are just different parity. So for one correlation function, you get 2 different states. So there's the forward correlation function, exponentially decaying, the mass, and there's a backward one, which is the negative parity state. If you have chiral symmetry, which means the light quark masses are zero, you can prove that the parity, you have parity doubling, so the masses are the same, the two parity states. In other words, the correlation function is symmetric forward and backwards. And the question is, do we actually get that in nature? Okay? Do we predict from QCD that you should have parity doubling? So here are our results. This is a correlation function of a log linear plot. As I said, the one correlation function gives you both a positive parity and a negative parity, positive moving forward, negative moving backwards. The different colours are different temperatures. So the black one is the lowest temperature, and the red one is the highest temperature. And you can see that the black one clearly is not symmetric. The minimum is well off 0.5. The horizontal axis is the percentage of the way through the lattice you are. But this red one here, the large temperature one, looks like it is symmetric. And if you just kind of colour in the data points which are at the minimum within areas, then you get those bars there, and you can see clearly that the correlation functions for the large temperatures become symmetric. So the actual correlation functions themselves, without doing any fitting at all, tell you the answer that you suspected, which is in the deconfined phase, the parity states are the same. So you get degeneracy between the positive and negative parity states. Okay, that's kind of pretty, but that's the thing that you look at by eye. Let's be a bit more quantitative. So you can just play games with numbers. This R ratio takes a difference between the positive part of the correlation function and the negative part at the symmetric point. And it takes a difference. So when the difference is zero, that means they're the same, which means you've got parity doubling. The masses of those two states are the same. When it goes to 1, that means they're very, very different. So it's maximally different. So here is this R ratio, and you can see for lowish temperatures, it's sort of closest to 1, depending upon which hadron you're looking at. But for large temperatures, it's close to 0. So that again is telling you the same thing, but a bit more quantitatively. We can do one step better. This is information which is a function of time. Let's just sum all these points over time. So we just get one point, one data point, one value at each temperature. And that's what this R ratio does, summed over time, with no time dependency. And these four boxes are at different amounts of strange quark content. So this is the one we're looking at before, but I can pull out one light quark and replace it with one strange quark, or I can pull out two and replace it with two strange quarks, etc. So the different strange quark content. And so this R ratio gives you 1 point at each temperature. So the horizontal axis is temperature, and you can see you get a typical kind of phase transition style of graph. You get something close to 1 here and something close to 0 here, and it has a transition around TC, around the deconfined temperature. So that seems to indicates very strongly that these parity states become degenerate pretty much right on the deconfined temperature. So you can extract the mass from the exponential fits. You can actually predict the masses of the positive and negative parity ground states as a function of temperature. So here they are again for the different amounts of strange quark content. The ones with the open circle are the positive parity states, and the ones with the full filled circles, filled symbols, are the negative parity states. So you can see something interesting. The positive parity states stay pretty much rock solid. They don't change with temperature. And it's the negative parity states that are starting high and different, but from the positive parity states, as a function of temperature, they decrease towards the positive parity partners. Okay, so we can do one more thing. I mentioned that the best way of studying this, in a sense, at non-zero temperature, is to look at spectral functions. Those masses I showed you in the confined phase. In the deconfined phase, exponential fits don't work anymore because the quarks are no longer bound, and you don't get hadrons, so you don't get exponential decays. You can study spectral functions though, and as time is pushing on, I will just jump to the conclusion, which is talking about, we use the maximum entry method basically to extract spectral functions. So you can imagine that in the confined phase, the spectral functions are just nice exponentials, and therefore you get a delta function for the spectral function. As you get the states melting away, the spectral function broadens out, and eventually if it's melted totally away, you'll get it all flat. So here are our spectral functions for the low temperature confined regime, and here they are for the deconfined regime. Different colours at different temperatures. So the dashed curves there are the lowest temperature we have. Okay, you can see a nice delta-like function as we expected. Importantly, there's both positive and negative energies there. I won't go into details, but the positive energy refers to the positive parity states, and the negative energy refers to the negative energy states. You get them both together in one spectral function. So here, clearly, you can see that the two parity states do not look the same. Okay? The masses are at different points, and the features are different, so they're degenerate, they're not the same. At large temperatures above Tc, they look a lot more similar. You get a symmetry between the two, which is telling you that the positive and negative parity states become degenerate, they're all the same. So here's my summary. So we looked at both raw data itself without any fits, and thinning exponentials, and even using the maximum entry method to get the spectral functions. And we have concluded that the positive parity masses pretty much are constant, but the negative parity states decrease with mass in the confined phase. And flipping to the deconfined phase, we see that there's a degeneracy, and so in baryons, the positive parity and negative parity correlation functions, information become degenerate, become the same. Okay?
In the first set of results you showed, not the spectral functions, are the higher hadrons above or below the decay threshold? So are they actually resonances, or are they all bound states?
They're all bound states. They can't decay. Our pion is our pi mass is 380 or so MeV. We've got another run at about 280. So pi mass is 380, and another one is, we've got two different runs, one for 230, so yeah, they can't decay. If they could decay, the spectral function would be really interesting to study, to see. I've always wanted to look at a spectral function where you can see decaying state, so you see the kind of ground state mass, if you like, and the state of the decay as well on the same spectral function. That's been my dream to see that one, and one day I might.
Okay, so if there are no more questions, just thank all those speakers again, and